So, this course is offered by NPTEL. I am Harshit Agrawal, a PMRF research scholar from IIT Bombay, and I will conduct weekly live session for the next 12 week for this course. So, just to start with, what is this session all about? So, these are doubt clearing session and interactive sessions. When it will be held, it's a weekly interactive session that will be taken by me every Tuesday from 6 to 8 p.m. Okay, till the course runs. How we will interact either by answering my questions in the chat box, asking questions in the chat box, or by raising hand, unmute, and asking your queries. And apart from live sessions, you can always use the discussion forum of the course to clarify your doubts, the answers to which will be given either on the discussion forum only or in the next live session. So, with these live sessions, you will be able to answer the graded assignments easily and also will provide you further understanding to the complex topics holistically. So, basically, we won't be discussing the graded assignment directly, but in indirect manner, I will tell you about the basic theory that you have read in the previous week so that you have much more clarity. And if you are not able to answer some question, then you can answer them next time. Okay. So I hope everyone are clear with about the session. So in today's session, we will first have a look at the introduction of this course. Then, where I will briefly describe what this course will be offering. Then we will head towards the discussion of for week one of the course. And fine, in the discussion section, we will discuss everything that we have learned in the week one of the course. And finally, we will conclude the course by just overviewing what we learned in week one. So let's start. So this course, Design of Reinforced Concrete Structure, is an introductory design course in civil engineering for structures made of concrete. In this course, we will discuss various elements of reinforced concrete structure, how they are designed, different design methods will be briefly discussed before introducing you to the limit state of collapse and serviceability. This is the main method that we'll be targeting throughout the course. And the main emphasis will be given to IS 456 guidelines. So the main part of the course is IS 456. By the end of this course, we will develop a thorough understanding about IS 456 guidelines. And it's a 12-week course starting from week 1 where we will discuss about introduction to reinforced concrete and different design methods, and by the end of week 12 we will discuss about limit state of serviceability. Okay, so let's look into what we learned in the week 1 of the course. So before moving into design of RC, we need to understand why we need designing. That is very important for clearing our basics. So as we'll all know, concrete is the second most consumed material on earth after water and is generally used for construction of several mega industrial projects. Some of the examples are bridges, crossovers, dams, buildings, as you can see all around you. Now, as you can see in the images, I have given you few examples of structures in India. Like these are the metro lines in Delhi. This is Matupeti Dam in Kerala, the largest concrete gravity dam. This is a 10-story, 12-story high-rise building in just near Delhi, and this is the famous Bandra Worli ceiling in Bombay, all made of reinforced concrete. So you can see what is the impact of reinforced concrete in our day-to-day life in construction field. Let me admit all the new joinees. Google Meet auto admission extension. Okay, I will see into it later on. Thanks for the suggestion. Okay, so these are the some projects that are very famous of reinforced concrete in India. Now, seeing these projects, though concrete will seem to be very durable. Like durable means it will seem that it is very long lasting and it will be in position for a long time. But due to improper construction practices and deterioration over time, concrete has a downfall and it fails before its intended period of service. Okay, now how this happened, let's see some examples. So here in the first image you can see a seven-story building collapsed in Thane. There is one example again of a structural collapse that happened in Pune, Maharashtra, and there is again one example of a six-story building that collapsed in Delhi. So one common reason behind all these collapse was use of substandard construction practice, construction material, and inadequate design. So, to have a safe and a reliable construction, we need to properly design a concrete structure. Now, before moving into design, now we understand that design is important. Without design, there are failure chances which can be critical for our society. So, before moving into design, we need to have a basic knowledge of different components of RC, of reinforced concrete. So, let's look at them one by one. So, as the name suggests, reinforced concrete is composed of two parts: concrete and reinforcement. By reinforcement, we mean something that which can strengthen the concrete, and that is accompanied by using steel rebar. Okay, but why do we need to strengthen the concrete? We will see it later. Okay, so this is like a reinforced concrete building. It has two part: concrete and steel. Okay, so let's see it both the component one by one now. First, we have concrete. So, as I said earlier, concrete is the second most consumed material on earth after water, and apart from that, it is the most consumed building material because it's cheap, easy to manufacture on site, and has good serviceability. And there are four main components of concrete: coarse aggregate, fine aggregate, cement, and water. However, apart from these four, there can be other component also like mineral admixtures, chemical admixtures, inert filler, but their use depends upon the application and need. For now, we will be focusing on these four components only. Now, each component of concrete plays a vital role in its design. So we will have a look at each component of concrete one by one so that we can understand the design of concrete properly. Okay, so first, we have coarse aggregate. Coarse aggregate are made up of various materials: gravels, crushed stone, recycled aggregate, and they occupy a large volume of concrete. Okay. Now, but how we basically define coarse aggregate? So, as the name suggests, coarse means something which is of larger size. So, these are the material which are larger enough to be retained on 4.7 mm sieve. Sieve sizes are like basically defined by Indian standards. So, 4.57 4.75 mm sieve, the materials which can retain on this are known as coarse aggregate, and their size can go up to 63 mm. Generally, for construction, we use 10 mm and 20 mm, but up till 63 mm, we consider aggregates as coarse aggregate. Okay. Now, along with fine aggregates, the total aggregate make up to 60 to 65% volume of concrete. So we can see how large volume they occupy in the concrete mixture. And within coarse aggregate also, we can have various type. There can be rounded aggregates, flaky aggregate, and angular aggregate. Rounded are like one which are almost rounded. Flaky are ones which have sharp. edges. These are angulars, and flaky are also kind of these only. So in these way also the aggregates can be classified. But what kind of aggregate we should go with? We should go with well graded aggregate, so that the pack they can properly pack inside the concrete. So if we have a concrete block, so if we have well graded aggregate, it can pack properly and it will provide minimum pores and maximum packing, which will help us to get maximum strength in the concrete. Okay, so we need well graded aggregates when we are talking about concrete structures. So this is what coarse aggregate are. Second component of concrete, it is fine aggregates. Okay, so as the name suggests, these are aggregate which are finer compared to the coarse aggregate, so they can pass through 4.75 mmc. The coarse aggregate retained on 4.75 mmc, they pass through 4.75 mmcs, and they retain on 150 micron sieve. Okay, how these aggregates are made of? They are made of natural sand or crushed stone particles. Natural sand is like, now we don't prefer use of natural sand that much because it is a natural resource which is depleting. So mainly we go with crushed stone particles, and these again with coarse aggregate make up to 60 to 65% of total concrete volume. Okay, so they occupy large volume in concrete. And just wait a minute. Since aggregates make up a large volume in concrete, we need to have a proper testing of aggregates before using, and for that we use IS 383 guidelines. Now, discussion about this is like out of course, so I will leave here only, but you should have a knowledge that there are proper guidelines which are available for testing each component of concrete. Okay, so these was all about coarse aggregate and fine aggregate, which make up the most volume of the concrete. Now, apart from aggregate, we have cement. Cement is the most important component of concrete. Why? Because it is the binder. What we mean by binder? Binder is something which acts as a glue, which helps to hold different components of concrete together. So we have coarse aggregate, we have fine aggregate, how they will be packed in the concrete properly, and how we will ensure that they do not displace or they do not break away with age. It is through cement, which act as a binder, which compact them properly and provide it a proper shape, which is good enough to take load later on. Okay, so cement is the most important component of concrete. And if we go by general definition, cement is a chemical substance which is used for construction that sets, hardens, and adheres to other material to bind them together. So we just discussed what is a binder and how it binds the concrete. Now, how it performs the binding function. We have said that cement is a binder, but how it performs the binding function? It is by reacting with water. So, cement, when it reacts with water, it forms hydrated products. And these hydrated products are the one which binds different constituents of concrete together. Okay. So, cement plus water gives us hydration products which binds concrete constituents together. So you can see here cement, water, and this is a paste, cement water paste, which will act as a glue for concrete. Okay. Now, just an additional point, while we are making a mixture design of concrete or making concrete, generally we express aggregates, both coarse and fine, and cement in kg per meter cube, or this much quantity we need, this kg we need, this much we need. But water is generally expressed in the form of W by C ratio. Why? Because it offers the inverse relationship to the strength of concrete. So if we say by a graph, suppose this y-axis represent the strength, and on x-axis we have W by C. So it is like inverse relationship. As the W by C ratio will increase, the strength decreases. So it's not like any amount of water we can take. The lesser it is, the more strength we will get. But it should not be that much less that our concrete is very stiff. It is not able to like take the shape or move. So while designing, we need to have a balance of W by C. It should not be very high, it should not be very low. And this makes designing a concrete a complex phenomenon. Okay. So now we are clear about different components of concrete. Now how concrete is designed. So designing of concrete is done based on strength requirement. Okay. So based on what strength of concrete we require, we design the concrete, and how it is represented. It is represented in the form of grade. Okay. So suppose we have an example. If someone says I need M20 grade of concrete, then what we mean, what this represents, M represents the mixture and 20 represents the characteristic compressive strength at 28 days in NPA megapascal or Newton per millimeter square. Okay. So we will understand what characteristic compressive strength means, why only 28 days and all now. Okay. So based on the grade of concrete, we can classify concrete into three types: high strength concrete, standard strength concrete, and normal strength concrete. Okay. Each classification of concrete has well developed application needs. High strength concrete is generally referred to concrete above M60 grade. M60 means the concrete which will have characteristic strength of more than 60 MPa. Okay, greater than 60 MPa. Now, where we find application of high strength concrete in critical structures or structures which are located in critical environment or which needs to be protected very well. So for them, we need high strength concrete. Then we have moderate strength or standard strength concrete. So this range from M25 to M55 grade. And where we find application, these are generally used in construction. So for construction, we generally use M25 to M55 grade concrete. Okay, general construction practices. And at the end, we have normal strength concrete, or we can also say low strength concrete. And these range from M10 to M20. Generally, below M15, now it is no more preferred to use concrete, but for low strength, we still say M10 to M50, M20 concrete. And these are generally used in pavement designs where there would not be much load which will be coming. Okay, so this is how we classify different types of concrete based on their strength requirement. And this table was taken from IS 456, table 2. Okay, for now, we just need to remember the application areas and where what grade is used. We don't need to dig deep into what do we mean by critical structure or what do we mean by less critical structure. With time, that will be cleared when we will read more about the course. Okay, so now in that example of M20, we said 20 is characteristic compressive strength is at 28 day. So we introduced two terminologies here: characteristic strength in 28 days. What is the meaning? What is the significance of these things? So let me take in students. So by characteristic strength, we mean the strength below which not more than 5% of sample will lie. Okay. How it is? So suppose we have 100 concrete cubes that we are testing for compressive strength. So more than 95 samples should be above 20 20 like should pass the M20 grade criteria to say that the concrete batch is following M20 grade. Okay. And why 28 days? Because it is observed that more than 99% strength gain happens in 28 days. Since cement is reacting with water to form hydration product, it is not like within a day reaction will be completed. It takes a lot of time, like it will go on throughout the lifetime. This reaction won't stop just after one day. It is a bigger, like, lifetime reaction. So it is generally observed experimentally or with experience. We have seen that above 99% of strength gain happens in 28 days. So that's why 28 days is taken as a reference for concrete grade. So at 28 days, if we are testing the strength of the concrete, we can say that this much strength is true for that concrete. Anyone is saying anything? If you have any queries, na, please write in the chat box so that I can see later on. Okay, so this was the significance of 20, characteristic compressive strength, and why 28 days. However, when we are designing concrete, we don't design for characteristic compressive strength. So we are saying that we need M20 concrete, so 20 is the strength that we require. But when we are designing concrete, we design for a target strength. Okay, so what is this? Why? So we are designing for target strength so that we can be on the safer limit, on the safer side. We can't say that the mix that we make will always have a 20 MPa strength, and we can't always cast like 100 samples or 30 samples to check whether 95% samples are passing the criteria or not. So just to be on the safe side, we cast concrete or we design a concrete for a target mean strength, which is given by characteristic compressive strength plus 1.65 times the standard deviation. What do we mean by standard deviation? So suppose we have casted 100 concrete, we have tested them for their strength. We got that they are passing M20 criteria, but not all concrete will offer the same strength. Some may have offered 20.5, some may have offered 22, some may have offered 18, some may have offered 20, 21. So there will be a little difference, though they were all casted with the same in the same batch. So we need to also have a value of standard deviation, what how the values were deviating. Generally, for estimating S, we need a minimum of 30 samples. Okay. But in reality, it is not possible that every time we can calculate the standard deviation and check the value. So code provides what standard deviation we can assume while we are designing our concrete. So suppose I say you that design a concrete of M25 grade. Now you will not do that. You need a standard deviation first so that you can get a target mean strength value. So you can refer to the codal guidelines and what standard deviation they have used. Accordingly, you can define your standard deviation, your target mean strength. Okay. So the code says for M10 to M15 concrete, standard deviation can be taken as 3.5. For M20 to M25 concrete, standard deviation can be taken as 4. And for above M30 grade concrete, we can take a standard deviation of 5. Okay, so using these data and using your requirement of concrete grade, which grade you require, you can have a target mean strength value for which you need to design the concrete. Okay, I hope everyone are clear with how the concrete designing is done based on strength requirement. Okay, so let's now look at some basic questions of what we have read in designing of concrete. Now, we are extensively talking about characteristic compressive strength, target compressive strength, target mean strength, how we determine the compressive strength of concrete. Can anyone answer in the chat box? What do we mean by compressive strength and how we determine compressive strength? I hope everyone are clear with the points that I have discussed till now. Okay, Varun, can you please elaborate a little? so that everyone else can also be clear. Yeah, you are correct. So, what we do, we cast concrete cubes. Generally, the code says that we need to have 150 cubes. I will have a new slide in between so that I can plot. Okay, so what we do, we cast cubes. Okay, 150 cubes, 150 side. Okay, and we check the compression strength of this cube using compression testing machine. So what is a compression testing machine? There will be a top plate, there will be a bottom plate, and we will apply load on this concrete, and we will see when the cracking occurs. So as soon as the cracking occurs, we will reach the ultimate load value. Okay, and knowing the ultimate load that the concrete can take upon the cross section area where the load was applied, we can get the compressive strength. So suppose we have an ultimate load of say 500 kilonewton, and we know the cross section area 150 cross 150 we can calculate what was the compressive strength of that cube. So this is how we determine the compressive strength, and generally we take three values of compressive strength and report an average value, because there will be certain deviation in the value, so we need to check for at least three cubes so we can be sure what was our compressive strength for the mixture that we chose. Okay, so this is how we determine the compressive strength of. Now you know that standard deviation value and what is your characteristic strength. So can anyone tell me what will be my target strength for an M25 grade concrete? Just tell me the value. If I want to design an M25 grade concrete, what should be my target mean strength? Okay. Anyone else? Okay. So 31.6 is the right answer. So when I want to design an M25 grade concrete, what is my formula of target mean strength? FCK plus 1.65 times standard deviation. So my FCK is 25 plus 1.65 times standard deviation. Standard deviation for M25 grade will be 4. So upon calculation, we will get 31.6 MPa. So suppose if you are testing 3 cubes for this design, the mean value of those 3 cubes should be above this value. If it is true, then you can say your design is for M25 grade. Okay. And finally, suppose I have 500 concrete cubes, then how many cubes shall pass the strength requirement for calculating the characteristic compressive strength? So suppose I want an M30 grade concrete and I have a batch of 500 concrete cubes. So how many cubes should pass the criteria of M30 so that I can say that that batch belongs to M30 grade? Okay, yes, 475 is the right answer. So we have seen in the earlier discussion not more than 5% sample results should are expected to fail. So from 500 cubes, 5% of 500 will be 25. So more than 475 samples should pass the strength requirement, then only we can say that it belongs to M30 grade. Okay, so this was like a basic discussion about what is how we design concrete based on strength and what we mean by strength. Okay, now we know that design of concrete is done based on strength, but how this strength will be achieved? What proportion of the components of concrete we need to take to achieve this strength? Okay, so what is the mixture proportion required for different concrete grade? That is what we need to understand now. So the proportion that we are choosing of aggregate, cement, and water should be selected such that we can ensure that when concrete is hardened, it achieve the required strength. By what I mean by concrete is hardened at 28 days. Okay, that is our reference. So, for a certain amount of coarse aggregate, fine aggregate, cement, and water, when I make concrete, so after 28 days, when I will do the compressive strength test, I shall get the required strength that I need. So that is how I need to take the proportions. Now, how we determine the proportions of cement aggregate and water? This is done by two ways. Either by designing the concrete mix, that is known as design concrete mix, or by adopting a nominal concrete mix, that is known as nominal mixture design. Generally, for M20 and lower grade, we go for nominal mixture design. But for higher grade, we need to design concrete completely, and that is done using IS 10262. Okay, now there is a lot of things that are there in IS 10262, but that discussion is not in the scope of this course because we need to focus more on the design of reinforced concrete, knowing that we have this grade of concrete. So we'll skip this part, but if anyone has any doubt, they can ask me later on in the discussion forum about IS 10262 or in any other ways. But right now, just remember, when we have a lower grade of concrete, we go for nominal concrete mixture where we know the proportion of what proportion of aggregate, cement, and water we need to take to get the strength. Okay. And for a higher grade, we need much more data so that we can say what how much quantity we need to achieve what amount of strength. Okay, so as shown in this table was taken from IS 456, and this shows for different grade of concrete how much quantity we require of different amount. So for different grade of concrete, we get different proportions. Okay, so you can see how much total quantity of dry aggregates we need to take per 50 kg of cement. So if we have 50 kg of cement, what is the quantity of maximum quantity of aggregates that we can take if we want to achieve this grade of concrete, and what should be the proportion of fine aggregate to coarse aggregate in that maximum quantity, and what quantity of water we need to take, everything is mentioned here. Okay, so quantity of water is in liter and everything else in kg. So this is how we design a nominal concrete mix. So if someone says that design a concrete for M10 grade, you can refer to this and check what proportions you can pick. So you will get proportion like 1 is to 1 is to 2, or 1 is to 2 is to 4. So this is how you get the proportion: cement, aggregate, water, cement, fine aggregate, coarse aggregate. And then later on, with the certain W by C ratio, you can calculate how much water is needed. Okay, so this is how you get the proportions when we want to design concrete for M20 gate or lower. Okay, so this was all about concrete. What are the components of concrete? How we design concrete based on strength, and what mixture proportions we need for getting that strength requirement. Okay, so let's move ahead, and now we will see into the second component of concrete, that is steel. Steel is an industrial product. Okay, concrete is something that we make on site, but steel is something which comes from industry and are used as a reinforcement bar in concrete. Now, what are these reinforcement bar? These reinforcement bars can be of different sizes, from 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, 25 mm up to 32 mm. Okay, which one to choose? It depends upon the type of the component and direction of placement of rebar. So type of the component, we have columns, we have beams, we have footings, we have slabs. Okay, we will discuss in the upcoming weeks about all these components. But for now, just for your information, for slab, we need 8. We generally use 8 to 10 mm dia bars. For columns and beams, we use 16 to 20 mm dia bars. Okay, so this is how requirement of the size of rebar change with the type of the component. Okay, now direction of placement of rebar, by what we mean by this. So there are two kinds of rebar. One is main reinforcement and one is tie bars. Okay, so main reinforcement is something that runs along the length of the section, and tie bars, they are used to just keep those main reinforcement in position. With the, like, when we will move ahead in the course, we will understand more about what is the requirement of main reinforcement, what is the need of tie bar. But for now, we need to understand that the main reinforcement are the main ones which for which we design, and tie bar we require so that our main reinforcement are in position and they are not getting displaced from their position or not getting disturbed from their position. Okay. Now, how size requirement vary with main reinforcement and tie bar? So generally for tie bar, we use a smaller diameter bars, 8 mm, 10 mm, and 12 mm. And for main reinforcement, we have a higher diameter bars, larger diameter bars, 16 mm, 20 mm, and 25 mm. So this is how size of the rebars change with the application. Apart from size, steel bars can also be classified based on their material: mild steel and deformed steel. So, mild steel are something which are plain and round, and they are mainly used in joints, contraction and expansion joints. And deformed bar are ones which have ribs. So, you can see here ribs are present on these bars. Okay, what these ribs offer, they don't slip. So when we have concrete and we have reinforcement inside the concrete, we need a good bonding here at the concrete rebar junction. A ribbed bar provides this good bonding so that these rebars don't slip. Okay, and properly bond with the concrete. Okay, so generally for construction practices we use deformed bars. Okay. And within deformed bar also we have two types of bar: thermomechanically treated and high strength deformed bars. So just for your knowledge, remember that we have two kinds of bars: mild steel bars and deformed bars. And within deformed bars also we have different classifications. Okay. Now, we have seen concrete based on strength. There are various strength of concrete and what we use and for what application. Similarly, for steel also, we can have different strength of steel. And how it is represented? For steel, it is represented through yield strength. Okay. So generally, the strength of steel is classified into three categories: Fe 500, Fe 415, and Fe 250. Fe means iron, and 500 is the yield strength of steel, which is represented in Newton per millimeter square. So, this is for mild steel, and this is for deformed or high strength steel. Okay. So, there are these three categories in steel also. Now we understand both steel and concrete. So steel is an industrial product, so don't need to design for it what is the composition of steel and everything. This we get from the industry. We demand we need 5 Fe 415 steel, so they will supply us that kind of steel. Okay, and the discussion of that is a completely different course which is on the design of steel structure, so we won't go into that. But just remember that we have different grades of steel and we have different grades of concrete, and for achieving different grade of concrete we design concrete using mixture proportion. Okay, now we understand both concrete and steel. So why we are taking reinforced concrete? We still don't know what do we mean by reinforced concrete. So the material concrete that we talked about till now is brittle, which is good in compression but weak in tension. So, what will happen if some load is applied on concrete and it has some edge support? So, what will happen? Suppose this is the neutral axis of concrete. So, the top part will be in compression and the bottom part will be in tension. So, since concrete is good in compression, here there won't be any problem. But in the lower half, where there's tension, there can be cracking, because since the concrete is weak in tension, it won't take tensile load very well. So it will crack very early, and which is not good for us. So that's why we provide reinforcement in the tension zone, such that why we provide reinforcement, because steel is ductile in nature. So steel can act as a reinforcement in concrete. So when load is applied on concrete, concrete will take the compression load well, and in tension zone, though there will be some cracking in the concrete, but those crack will be blocked by the steel reinforcement, as the steel will start to yield and it won't let crack to propagate further. So this makes concrete a stronger material, and that's why we need reinforced concrete. Okay, so I hope this is clear to everyone why we are going for reinforced concrete. Okay, so this was the main reason why we need reinforced concrete. Okay, and why we need to design, so that we can know how much material we will need, how much material of aggregate, cement, water, how how many rebars we need. For this, we need to design a reinforced concrete, and within material also, what are the size and the type of the material that we need. Okay, apart from this, there is one more factor that for which we need to design: how much cover we need to provide. Now, they why we need cover? Because of durability concern. We see these reinforcement that we are providing inside the concrete na, they are prone to corrosion. Corrosion is something that can't be stopped when we are talking about steel. So we need to provide steel somewhere inside the concrete so that it is not corroded. Okay, so we don't have any durability concern, and our structure can perform its activity till the intended lifetime that we need to design. Now, discussion about corrosion and how durability comes into account, we will see slowly in the course. But for now, remember, we need to design concrete for how much cover we need to provide, and what are the amount and the type of material that we need. That's why we need to design the concrete. And apart from designing, we also need detailing, where to provide the reinforcement. When we are talking about detailing, we need to talk about how we are providing the reinforcement. So suppose this is my concrete element. Reinforcement can be provided at the bottom also, at the top also. Where to provide the reinforcement, that we need to know. Okay, because when the load is applied on the concrete, this is compression zone, this is tension zone. So in the tension zone, we need reinforcement. So detailing is important, where and how many reinforcement we need to provide. Okay. Apart from this, suppose this is a column and this is a beam. Now this is the junction of beam and column. Okay, there will be slab also. Now each element will have their own reinforcement. Okay, that will be running throughout the element. Okay, now at this junction it will become very complex. Many bars of different diameters will be coming at the junction. So we need proper detailing so that here there is no mishap in our design. Okay, so for that we need to have a proper detailing. So both design and detailing are important when we are talking about reinforced concrete. So basically in this course we will talk about designing of concrete, and for detailing we have certain other codes that we follow. Okay, now since we have discussed a lot about concrete and reinforcement and types of concrete and composition, there are two other important factors also that we should be aware of. One is formwork and other is curing. So formwork, you can see these wooden sections that you can see. So formworks are something which provides strength to the reinforced concrete until it has gained enough strength. Okay. So these are provided initially during the construction. And curing is basically supply of water. Why we are supplying water? So that there is no loss of water from inside the concrete. Okay, there is no cracking. So these are just some additional points for your understanding that you should know. Apart from concrete and steel, there are two more important factors when we are designing a concrete or designing a reinforced concrete structure. Those are formwork and curing. Both of them plays a very important role. Okay, so this was all about reinforced concrete as a material. Okay, during this course, we'll focus on IS 456 guidelines. Okay, now there are five sections in this code. First section will talk about general introduction to reinforced concrete and different materials. In second section, we will talk about material workmanship, inspection and testing of those material. In third section, we will start discussion about the design considerations. If you will read this code, the code is freely available. You can download it very easily. So in the third section, we'll start the discussion about general design consideration. In the fourth section, we'll come across special design requirements for structural member. And finally, in the fifth section, we'll talk a little about structural design in terms of limit state method. Okay. One by one throughout the course, we will be exploring all the sections, but you can also read the code by yourself so that you can have a very thorough understanding about the code. It is a very important code when we talk from a civil engineering point of view, and everyone must be clear with every clause, every table, and every line written in the code. Okay. Now, I have talked about design, detailing, and everything. So, apart from IS 456, there are other important codes also that we must have a knowledge of. Say, some of those are IS 13920. In our course, we will focus on 456 only, but this is for just for your knowledge. IS 13920, which is used for designing in earthquake prone structures. There is IS 875 that we will also use, and it is used for calculation of loads that are acting on a structure. And there is IS 1893 again for earthquake design. So, and also we talked about IS 10262, which is used for mixture proportioning of high strength concrete and all. Apart from this, there are certain handbooks also that are available, which can make designing and detailing of concrete very easy for us. So you should also be aware of these handbooks. Okay. Now let's look into the topics of IS 456. And first, this week we'll talk about different design methods of reinforced concrete. Okay. Now, before moving into different design method, just remember what is our aim. We have three aims when we are designing reinforced concrete. The concrete should be safe in terms of strength. The concrete should have minimum serviceability when we are talking about its durability, and it should be cheap. It should not be very costly. Okay. So based on these three aims, we have three design methods when we are talking. What do we mean by design method? How we are designing concrete. You will see what is the difference in these three methods. But for now, remember that there are three design methods. First one is known as working stress method. Second is known as ultimate load method. And third one is known as limit state method. Okay, we will see one by one a little introduction on all these three methods of design. This week we will just have an overview. From next week we will start our discussion with working stress method first, and slowly we'll move till limit state method. Okay, now first is working stress method. Okay, or it is also known as modular ratio method. This is a very old method. It was like proposed around 100 year ago, and also it is based on linear elastic theory. So it consider concrete till elastic limit. If we plot a stress versus strain profile, so there will be an elastic portion and there will be a plastic portion. So working stress method considers till elastic portion. Okay, it is considers material to be very performing linear behavior till elastic motion, elastic limit. Okay, and in this method, it is assumed that structural member behaves elastically, and due to working load, stresses are within the elastic limit, and we define stresses with a proper factor of safety. How we say that stress developed should be less than the allowable stress or permissible stress. So when we are designing a member, we ensure that the stresses that can develop on the member should be lower than the allowable stress. And how we get the allowable stress? Using the yield stress of the material in the factor of safety. Okay. So for different elements, for concrete we'll have different factor of safety. For steel we will have different factor of safety. For concrete is generally in working stress method it is taken as 3, and steel it is taken at 1.5 or 2. uh, I'm not very sure about this factor, but generally in this range we take this factor of safety and we determine what is the permissible stress for a particular concrete member. And when we are designing a concrete, our working stress that is acting on the member should be less than the permissible stress. If it is not, then we need to modify our design. Okay. Now, what is the problem with working stress method? So, since we are considering load till elastic limit only, load, what happens if the load is exceeding the elastic limit? So we are not considering serviceability into account. Okay, we are only limiting the load application till the elastic limit. We are not taking the plastic limit into action. Okay, so this is one problem. Second problem is, since we are considering very low range of load limit, we will need to design a very heavy. We will have a very heavy load design. Like permissible stress in our case will be low, so we need to have a very heavy load design so that our working stress is less than the permissible stress. We need to design a more stronger concrete, more stronger reinforced concrete than we should have designed. So this will make our structure less economic. And also, since we are just talking about the working loads, we are not taking into account different types of load. What are different types of loads we'll see shortly. But again, remember, this is one more drawback, that we are not able to discriminate between different types of load that can act simultaneously on the structure. So these are three main drawbacks of working stress method. Though it is very simple, so it is preferred, but it has its own drawback. So we will see on field where we can use working stress method and where we can't use working stress method. You will find with several cases where working stress method is used, but again you will also find several cases where it is not used. Okay. Second is ultimate load method, or known as load factor method. Now, working stress method was elastic design. Ultimate load method is plastic design. Why? Because it takes ultimate load into account. In working stress method, we were taking just the load till the elastic limit. Okay, till yielding point. Okay, this is known as yield strength. Na? So we were taking load till yield strength only. But in working ultimate load method, we are taking load till ultimate limit. So in this method, ultimate load is obtained for enhancing the service load by some factor. Okay. So there what we did, we defined we knew the yielding yield limit or elastic limit, and for upon that we applied some factor of safety to get the allowable stress. In this, what we take, we know the ultimate load, we multiply that ultimate load with the some factors, and then we define the our load that we need to take. So this will be some load multiplied by some factor, and this will be the ultimate load for which we will design. Now, going till ultimate load, what it helps us to provide a more economical design because we are considering the ultimate limit of the structure. But here, one problem is there. We have assumed that we know that concrete won't take tension into account. So when we are going beyond elastic limit, since there is due to load, we have crossed the elastic limit, then under high load, tension stresses can develop and it can show cracking, which we have not taken into the account during this design part. So this can be become a problem, and this can lead to serviceability issue. We'll have a much more deeper discussion upon how ultimate load, how structures are designed for ultimate load and all. But right now, you need to remember only two things. Ultimate load is defined for using plastic design, and it again is not it though it is more economical than the working stress method. It again doesn't take serviceability issues into account. Okay, so it is better than working stress method, but it also has its own limitations. Okay, now finally, we have limit state method of design. So we know both working stress method, in which we were taking elastic limit. In ultimate load method, where we were taking plastic limit. Third one is limit state method, and this is the most appropriate one. In this, it is more advanced than any other traditional design philosophy. Why? Because in ultimate stress method, calculation were done using working load. In working load method, calculation were done using a working load, and then ultimate load method calculation were done in ultimate load. But in limit state method, both ultimate load and working load will be taken into account. Using ultimate load, we will get the safety against in terms of strength, and using working load, we will take into account the serviceability. Okay, so both strength, safety, and serviceability you will take into account. So this will make our design both economic and durable. Okay, now what is this limit state? What do we mean by limit state? Okay, so limit state is nothing but acceptable limit of safety and serviceability requirement. So if we are designing a concrete and we know the limit state, so our design should pass this acceptable limits criteria, so that we can say that the structure is safe and serviceable. Okay, so by limit state of safety, what we mean, the strength, the limit state of safety, what it says that for this we take the worst load combination and accordingly we design the concrete. And in limit state of serviceability, we check whether the structure is performing satisfactory under working load. Okay, so that the people inside the structure is comfortable. So limit state of strength, in this we take the worst load combination and design structure for taking that kind of load. And in safety, we check whether the structure is performing safely or not under the working load. Okay, we'll have a deep discussion upon limit state of strength and serviceability, but for right now, you should know the both the terminologies and why we need both the terminologies. Okay, now right now we talked about working load, ultimate load, load combinations. What do we mean by these load combinations? So when we talk about a structure, there can be different types of load that can act on the structure. There is dead load, the load due to elements that are fixed inside the structure. These live load, these live load can be due to the residents inside the structures and all. There can be wind load that is acting from the exterior of the structure, and there can be earthquake load due to earthquake seismic activities. So when we need to design a structure, we should know each type of load that can act on the structure. Generally, we take either wind load or earthquake load. Why? Because there are very less chances that both wind load and earthquake load will act simultaneously. So we take one of either, which is more critical to us. And what are load combinations? These are set of various loading conditions that can act together on a structure, for which we need to ensure safety and economy of the design. So as per IS 456, when we are talking about limit state of collapse and limit state of serviceability, this is how we can combine different loads when we are designing a concrete structure. So suppose if there is only dead load and live load, we can take dead load plus live load and multiply them by a factor of safety of 1.5, while keeping the wind load as 1. Or we can combine wind load and dead load and wind load with these factor of safeties. Or if we have all three acting together, we can take this factor of safety. So this is for collapse, limit state of collapse design. And when we are designing for serviceability, we can take these factors. Okay, so these are how safety factors are taken for different load combinations. Okay, so I hope everyone are clear with different design methods and different types of loads and loads combination. If everyone are clear, we will see two numericals so that whatever we have read in this course, it is clear to everyone. Okay. So this is first question for you. There are different live load acting on a structure under a given condition. We need to determine the characteristic load. Okay. So these are the loads. Try to calculate the characteristic load. Everyone are clear with what all we have discussed right now till now. Okay. Try to solve this question then. And even if you are not solving, tell me the steps how we will achieve the characteristic load. Like if anyone has confusion with what we mean by characteristic load, we can also take you can also understand it by target load. So if these are the loads that are acting on the structure, what should be my target load for which I should design the structure? And how you got this value 38.2? What topic you have confusion? Just please elaborate. Okay, I will wait for 5 minutes. Everyone try to solve the value that I have received in the comment section right now. Both are incorrect. Okay, try to understand what we mean by target load. What was target load? The mean strength plus standard deviation that we take into account. Okay, now try to think the load below which not more than 5% sample should fall, right? So I have five loads. I have not told you what grade of concrete I'm designing or anything. Now think about that and do the calculation. You're very far away from the correct answer right now. I will like be on mute for 5 minutes, and in 5 minutes you will start the solution. By that time you think how to solve. Okay, so let's see the question now. Now, in this question, what was said to us that we need to calculate the target load. Okay, so what do we understand by target load? Okay, characteristic load or target load. What we understand by that? So, characteristic load is something below which not more than 5% of sample will lie. Now we define the target load by characteristic load plus 1.65 times standard deviation. Okay, how we will get this value? We'll get this value by determining the standard deviation. So this can be taken as the mean, and this can, for which that we need to define the standard deviation. So suppose if this is our distribution, okay, and this is our mean value of load. So and this is 1.65 times standard deviation. So if I assume that my data points are distributed normally, then above this limit, mean plus 1.65 times standard deviation, not more than 5% of cases will lie. So if above this limit, not more than 5% of cases are lying, so this will be my characteristic load value. Okay, everyone are clear? This value we will get by calculating the mean, and this value we will get by calculating mean plus 1.65 times standard deviation, and this will give us the value of characteristic load. How we define the characteristic? That's when above which not more than 5% of cases lie. So again, above this also not more than 5% of cases will lie if we consider our data is distributed normally. Okay, now how we'll do this calculation? I hope everyone are clear with what I mean by characteristic load. Characteristic load. Okay, so I will get the target load or characteristic load that we are talking by calculating mean plus 1.65 times standard deviation. Okay, what is my FM? FM is nothing but 30 plus 15 plus 20 plus 45 plus 50 divided by 5. So how much it will be? So how much it will be? 32. Okay, 32 kilonewton per meter. Now this is my mean value, FM. I will get that standard deviation. So standard deviation for a small set is determined by square root of, I shall use a pen to write that formula. So standard deviation is determined by square root of F minus Fm whole square, summation of F minus Fm whole square upon n minus 1. Okay, so this is the formula that we use for calculating the standard deviation for a small set. Right now we don't have a big set, no, whole 30 samples or 100 samples. This is a small set, so that's why we use this formula. There are two formulas: standard deviation for a set and standard deviation for a range of data. For that higher range of data, there is not n minus 1, there is only n. But for a smaller set, we take n minus 1. Okay. So f we know 30, 15, 20, 45, and 50, and fm we know 32. So it will come out like this: 30 minus 32 square plus 15 minus 32 square plus similarly everything else upon 5 minus 1 whole and under root. Okay, so if you will do this calculation, what you will get, standard deviation value will come out to be 15.124. Okay, now we know the standard deviation and we know the mean load. So our characteristic load will be 32. Where is my pen? 32 plus 1.65 times 15.24. So it will come out to be 54.16 kilonewton per meter. Okay. Why this value is so high compared to mean? Because the load acting on the structure is also very different. Somewhere it is 50, somewhere it is 30. So to be on a safer side, our target load or characteristic load should be 54.16 when we are designing, so that the structure can take all kinds of loads that is acting on the structure. Okay, if my load would have been 38 or something that was reported in the answer, how it will take 50 kilonewton, 45 kilonewton load? It would fail in these cases, no? And how you thought that it is only in 5% of the cases where it is exceeding the limit? So there should be a proper way to do the calculation, and this is the calculation. This is the main formula. Okay. I hope everyone are clear with how I calculated mean, how I calculated standard deviation, from where we got this formula and how we got this value. Okay. Any doubts in the solution? Okay. So let's see the last question for today's class. Okay. The question says calculate design load in collapse and serviceability separately for this given conditions. Okay. So we need to calculate the design load in collapse and design load in serviceability. I will keep this slide on and I will paste this figure for your reference. Okay. Try to do the calculation on your own. Okay. So we have different values of dead load, live load, wind load, and earthquake load. And we need to calculate the design load in collapse and in serviceability. You know how what factors we take into account for different kind of loading condition, and we know that in between wind load and earthquake load we take only one. So you know, seeing the value, which one you need to take. Try to do the calculations. I will wait for 5 minutes and then we'll see the solution. Okay, I will mute myself and I will turn back on the slide so you can see the values. Okay, I got two values. I I got two values from you guys. Let's see. For serviceability, you are saying 237. Okay, we'll see. I am expecting more answers. Okay, so let's see the solution now. So we have these loads. Okay, and we need to find the design load in collapse and in serviceability. Okay, so first we will see collapse and then we will see serviceability. Okay, so in collapse, what all different cases we can take? First case is taking only dead load and live load. Second case is taking dead load and wind load or earthquake load. And third case is taking all three loads. Okay, so what we do, we take all different load combinations with their factor of safety. We get all the values, and the maximum of all the three cases we take as the design load. Okay, so let's see what value we'll get. Okay, for design load in collapse, first case is dead load and live load. So for that, factor of safety is 1.5. So 1.5 times dead load plus live load. So what value it will give me? 1.5 times dead load is 100 and live load is 150. So it will come out to be 375 kilonewton per meter. So this was first case. Now second case is dead load plus wind load or earthquake load. Okay. So now either wind load or earthquake load we need to take into consideration. We don't need to take both. So you can see in the guidelines here it is written. While considering earthquake effect, substitute earthquake load for wind load. So since our earthquake load is more than wind load, we'll take earthquake load so that we have a safer design. Okay. So second case will be wind load, earthquake load plus dead load. So again the factor of safety are 1.5 and 1.5. 1.5 or zero point 0.9. Zero point 0.9 is written if the value is considered stable against overturning. Right now we will take only 1.5 because no more information is given to us. So it is dead load plus earthquake load 1.5 times. So it will come out to be 1.5 times 100 plus 22. So what it will yield? 122 into 1.5, 183 kilonewton per meter. And third case is when we take all three loads into account. Okay, so for that we have 1.2 times Dead load plus live load plus earthquake load. We won't take wind load. Okay, so it will be 1.2 times 100 plus 150 plus 22. So what it will yield? 326.4 kilonewton per meter. Now, what will be my target load? Seeing all the three values, we'll use the maximum of three values. And what is that maximum? 375 kilonewton per meter. So this will be my design load in collapse. Everyone got how we use loading factor into account and how we take all different cases. Okay. Similarly, we'll calculate design load in serviceability. Okay. In that again, how we'll take things into account. First combination is dead load plus live load. Okay. So what it will be? 100 plus 150. So it will come out to be 250 kilonewton per meter. Second case is dead load plus earthquake load. I am taking just direct summation because factor of safety is 1 in case of serviceability. Since we are only targeting with the target load which is lower than the ultimate load, that's why we take lower factor of safety when we talk about serviceability compared to safety. Okay. And finally, we have the combination of all three, which is 1 into dead load plus zero point 0.8 times live load plus earthquake load. So it is 100 plus zero point 0.8 times live load plus earthquake load, which will come out to be 237.8. Okay, so what is the maximum of three values? 250 kilonewton per meter. So this is what will be my design load in serviceability, and this is my design load in collapse. So what answers I got? Okay, there were some unknown answer. Okay, Varun, you considered only the last case, the combination of all three. But when we are talking about load combination, we need to take all load combination, all possible load combination. Earthquake load may act or may not act, but dead load, while live load may act or may not act. So whenever we are calculating the design load, go with all the loads combination and take the maximum of those loads. Okay, and this is how it is done. Okay, I hope everyone are clear with how we calculate design load in collapse and design load in serviceability. Okay, so with this, we will conclude the first week of the live session. So in this week, we first discussed why we need to design reinforced concrete. We saw some example of reinforced concrete structures and what are the problems, some damaged reinforced concrete structure. Then we had an overview of reinforced concrete. We discussed about concrete, its component, design method based on strength and mixed proportions, nominal mixture design. Then we discussed about steel and its classification based on bar diameter, based on type of steel, mild steel and HYSG steel, and based on strength, Fe 250, 415, and 500. Okay. Once we discussed about both reinforcement and concrete, we discussed why we need reinforced concrete because concrete is brittle, and if load is acting, tensile cracking can occur. So that's why we provide reinforcement at the bottom, which can take the tensile load. And then we discussed why we need design so that we know the quantities and all, and why we need detailing so that we can properly design where to place the reinforcement and how to design the joints. Okay. And at the end, we discussed different design method, working stress method, ultimate load method, and limit state method, and we saw load and load combination, and based on that we saw couple of numericals. Okay, so I hope the discussion of the week is clear to everyone. If you have any doubts, I will be there in the meet for next 5 to 10 minutes, else you can ask the doubts in the discussion forums always. Thank you. Yes, the PPT will be shared to you by the NPTL team. We need to share the PPT with them and then they will share it with you. Don't worry. It depends upon your university and all. Generally, code books are not permitted during the exams. For NPTL exam also, I don't know whether the code book are permitted or not. But when you will like proceed on with this course, by time you will remember all the values, so it won't be a problem. With time you will remember everything. Live recording it will be shared to you by NPTL, or you can always go on YouTube and search for design of reinforced concrete, and you may will find my recordings. They will be uploaded on YouTube. You can follow the channel and so that you are regularly updated with the videos of this live session. uh, as I told na, standard deviation how we calculate, there is a formula for standard deviation calculation, which is summation of value minus mean square upon n minus 1. So if we know number of loads, live loads that are acting on the structure, suppose there are 5 loads, so n minus 1 will be 4. Mean we can always calculate, and for each value we can calculate the summation, and we can calculate the standard deviation. Okay, just remember this formula. If I can write it again, square root of summation of f minus fm square upon n minus 1. So this is how we calculate standard deviation. Remember this. Limit state of collapse, like loading, the case of loading that we are taking different. In limit state of collapse, we are going till ultimate load, and for serviceability, we are taking only working load. Okay, now what's the need to calculate load? Limit status collapse is always high. This is generally done for like different safety. Like for serviceability, we generally don't take much into consideration because our main purpose is to design structure for safety. But serviceability, minimum serviceability is also important. So that's why we take certain lower load limit for serviceability. When we will proceed on with the code, you will get a better understanding about what do we mean by serviceability, how we access serviceability, why we need to take a different loading condition for serviceability. Wait, with time these all doubts will be clear to you. Right now we have not taken much deep understanding about what is collapse, what is serviceability. When we will get into that topic, the things will be getting much more clear to you, and by that time if you won't understand, you can always ask me back. Method in which permissible stresses are kept well below the material stressor. What is this method? What method you are talking about? Limit state. That is working state method. Okay. So this was that method that we talked about. Okay, working stress method. So generally in working stress method, we consider that concrete can take load only till elastic limit. And based on that, we define different factor of safety for concrete. And similarly for steel also, we take till yield strength, define factor of safety, and we design concrete for taking stress lower than that stress. Okay. Next week, we will have a very brief discussion upon working stress method. Lengthier discussion, we will see of several numericals also. So by that time, you will get much more clarity. But right now, what is important for you to know? There are three design methods. Working stress method, it is takes till elastic limit. Ultimate load method takes load till plastic limit, and limit state method, it takes both ultimate load and working load. For safety, it takes ultimate load, and for serviceability, it takes working load. Okay, so just remember this for now. With time, things will get much more clear to you. I could have answered in a better way, but some of you will understand, some of you won't understand. So let's move on with how the course is designed, and things will get clarified to you. Next live session, my live sessions will run every Tuesday from 6 p.m. to 8 p.m. for next 12 weeks. So next live session will be on next Tuesday. YouTube channel name, sir. There is no such specific name that you will be shared that information from NPTL. Don't worry. All you can always search Harshit Agrawal, designer of reinforced concrete. You may get the channel directly. The channel YouTube, all these live recordings will be uploaded on YouTube so that you can watch them again and again what was discussed. The PPT also will be shared to you. So just wait. I guess NPTL will share all the details with you with time. So you just need to wait for them. If anyone they don't are not able to find the YouTube channel link, by next week I will share you the link. Okay, so if there are no more doubts, we will close the session for now, and we will meet next week now. Thank you.